Okay, so to start our next unit out here, we're going to motivate the topic with a problem. This is a classic problem, a variation on it, and I'm going to call it the inheritance problem. So don't forget to take notes here. Imagine your long-lost Uncle Clemson has left you an inheritance. Knowing how much you love math problems, he left you with two choices over the course of the next 26 years. Why 26? Good question. I don't know. Option one, you can have $10,000 right now and then $1,000 more each following year. So next year you'd get 11,000, and then after that you'd get 12,000 that year for 26 years. Option two, you get 1 cent now, and the amount you get each year is twice the amount from the previous year. So that means next year you'd get 2 cents and then 4 cents and then 8 cents. And I want you to go ahead and think about, what your gut tells you you'd choose. It might kind of seem obvious right now, but we'll get to thinking about that through this problem. And I want to mention that there are some things that you'll want to know, prior knowledge. So you may want to go back and look up some of these things to remind yourself what they are or how to use them or how to do them. So difference tables, finding a closed form rule for linear, quadratic, and exponential functions specifically, and a little bit arithmetic and geometric sequences and what they are, but mostly difference tables, and then finding closed form rules. We've learned methods of doing that. So let's go ahead and get into the problem. Okay, so now that you've thought about the inheritance problem just a little bit, and I'm hoping you took the time to really think deeply about it, I have some guesses for what you maybe thought right away. First of all, option one is clearly better from the start, right? Because if you're getting year one $10,000, you're automatically better off than you are in year one here. But you should be familiar at this point a little bit about linear versus exponential growth. And I'm hoping you've realized that option one is a linear growth pattern because you're adding the same amount each year. We've also realized that can be thought of as an arithmetic sequence. And option two happens to be exponential growth because of this thing. We're doubling each year, right? We get twice the amount the previous year had. And that goes with a geometric sequence if we're thinking about sequencing of numbers or sequences. And now I'm going to pose you a couple more questions to dive in deep and really try to actually answer this problem. And we're going to use a new concept that we're leading into with this problem after this, okay? I want you to do these two, okay, on your own first, okay? So I'd like you to pause the video and find a closed form rule for f of t and g of t. And notice we're calling option one f of t and option two g of t. T for time, the number of years that pass. And then also for which values or value of t is f of t less than g of t. So we're saying, when is this amount of money going to be less than that, and when is this amount of money going to be greater than that? You can probably easily just know certain values. You could even make a table and list it out. I think a graph might be helpful. Maybe the closed form rules you make will be helpful. So go ahead and pause now and answer these two questions. Okay, so let's actually go over these together right now. Let's first find a closed form rule for f of t and g of t. So for f of t, let's just make a table, and maybe you don't need this. You can skip ahead if you think you got this. Just check your answer though. We know that when t is, let's say, 0, meaning right away, let's say $10,000, and then 1 is going to be 11,000, 12,000, for 2, etc. We've realized that a difference table is helpful for these. And you can see where that $1,000 comes in. Now, of course, if I keep going with the years here, we can see how it's adding up. But your actual answer for this, you should check, should be f of t equals 10,000 plus 1,000 t. Now, of course, it's okay if you put the 1,000 t first. It doesn't really make a difference. And then if we do a similar thing here for t and g of t, we can see that 0.012, we have 1 cent, 2 cents, 4 cents, etc., which is really slow going right now, at least in the beginning, right? And we've learned to make a ratio table of these. Well, this is just doubling each time, right? And your formula for g of t, let's write that here as well, is going to be, well, 1 cent times 2 to the power of t. Parentheses don't really matter here, but just because there's a decimal there, if I put a dot there, I just feel like it might be a little bit confusing. Okay, so there are your two functions here. Now here's the trick. Let's move to number 2. For which values of t is f of t less than or f of t greater than g of t? Okay, and what we're really asking here is, which option is the better choice? And which year does one surpass the other? And I think we can kind of answer that a little bit over here because we can see that g of t starts out obviously less, right? So we know starting at year 0 right now, g of t is less until when? That's the key. Where's that spot where the amount you get under option 1 and 2 are exactly equal to each other? Okay, so it's actually important to know when f of t equals g of t. What I mean by that is figuring out what year, which t value makes these two functions equal. So this is equivalent to saying, when is 10,000 plus 1,000 t equal to 0.01 times 2 to the t? The problem with this right now is this is linear, that's exponential. We haven't really done much by hand to figure out how to solve an equation like that. But you know what? Right now that doesn't matter too much that we can do it by hand. We're actually going to pop over to graph and we're going to solve it in that way. Okay, so let's go ahead and do that right now, and then we'll get to an extension of this problem. Okay guys, so let's look at this example on a graph. I'm using desmos.com/calculator. There's also a Desmos app that's really easy to use, especially because we're going to have to do some zooming out. Since we're going to do all of our examples here, I'm going to make a folder here, and 1 and 2, and then press enter, and then all the stuff below when I press enter are going to be in the folder. Desmos doesn't really like t as an input variable. It's built to use x, so I'm going to do 10,000 plus 1,000 x as my first function. I'm going to press enter, and then g of x equals 0.01 times 2 to the x. And so we can see here, I think I reversed those from when I draw this on the board later, so let's switch those colors. You can see here that, well, this almost looks vertical, but it's just because it has such a steep slope at 1,000, and you can see that our scale is equal on the x and y axis. But since these functions are growing so quickly, I'd really like to shrink this y-axis, and I want to leave the x-axis alone. On a phone, it's really easy. You can just pinch and zoom just the y-axis, but on the computer, I have to go into this settings, and I'll leave this alone, the lower bound for the y-axis, but the upper bound for the y-axis is easiest. I think I'm going to do 50,000 because I know this is getting really big really fast. And sure enough, that looks pretty promising. So all we got to do is, here's f of x, or f of t, I guess. Here's g of t. And remember how we said we're looking for the crossing point. Desmos easily just tells you right where it is. So we can see that we already kind of talked about how the option 2, g of t, grows slower at first, but it very quickly, right, almost 20 years passes option 1. And we'll go back to the whiteboard now and finish talking about this. So again, to finalize this, if we looked at the graphs of the two, we saw on the graph that they cross at 21.591, 31,591.086. And again, that 591 and 591, they're entirely coincidental. We can clearly see that g of t is less than f of t, like we talked about, up until almost the 22nd year. Okay, which means we haven't finished off the whole 26-year inheritance we're supposed to receive. And so we can, I think, answer this question now, okay? So we can see where they cross, and that means we know where the one is less than the other, and vice versa. Now, it's interesting that they do cross again back here, but that point's irrelevant because that represents negative t-values. We're not really going back in time in this case. It doesn't really make sense in this context. So we can answer this fully now. When is f of t less than g of t? Well, f of t is less than g of t. Actually, that looks like it's after this, right? So when t is greater than, right? When t surpasses 21.591, that would be the solution to this. And then, again, since we have to ignore this, it's kind of outside of the domain here. From 0 until there is when g of t is less, or when f of t is bigger, okay? So we're going to say t is between 0, or equal to 0, actually, and 21.591, okay? So now I have all the information we need on what would be the better option. If I'm about to die within 22 years, or that's likely, then maybe I want to choose f of t, I think, because f of t is bigger within the first 22 years. But if I'm actually planning on receiving my full inheritance, it looks like that option 2 would be better because g of t is actually going to be much greater once I pass that. Okay, so let's go ahead and move on to a new way of thinking about the same problem. Okay, so I have to apologize. I tricked you guys a little bit. Maybe you already suspected this. You might have already been thinking, well, we had a little bit of a problem in the last question we were asking, because remember, we're trying to figure out which option is best, and since the problem statement itself said that each year I'm given however much, well, my inheritance is actually the total of all that. It's not just what I get in 1 year. So what we did last time turned out to only give me the solution to when my amount I get in that year surpasses. And so that's actually a different problem. So we're interested in the accumulated total, not just individual years. That's what we're going to solve next, okay? So let's go ahead and let f of t and g of t, but capitals this time, and that turns out to be a typical notation or thing we do when we're doing problems of this type, where we're summing things up. You'll see that later on in calculus even. Be the total amount received by year t. Okay, so we're still using f for option 1 and g for option 2. And let's go ahead and answer the same questions from numbers 1 and 2 that we just did, but for these functions instead, the accumulation functions, okay? Now, I want to remind you, we're going to still be using some processes that we've done in the past to figure out a closed form rule. So that's what we're going to start with, is finding a closed form rule for f of t and g of t, okay? But big F and big G. And then we'll go ahead and ask the same question. When is it worth it, I guess, or for which years is option 1 going to be less than option 2, and then for which years is option 1 going to be more than option 2. Okay, so let's start with the rules. Again, I want you to, like usual, before we start this out, I want you to actually try to do this yourself first, okay? So after we fill out together the total column here, I want you to try to remember how to find a closed form rule or what strategies we could use. And the same thing for this one, okay? So please make sure, it's really important that you are pausing your video and trying to wrestle with this a little bit yourself and figuring out before we continue on. So let's start with this one here. Remember that big F, I already included the outputs up to 5 for little f, is the total. Right now my total is actually just 10,000, right? But then when I add 11,000, so it's going to become 21,000, if that makes sense. And then when I add 12,000, that's going to become 33,000. And then this is going to become 46. And then plus 14 is 60. Plus 15 is 75. Let's throw in the zeros there. Okay. Now, again, this is where I'd like you to pause and actually try to think, what strategies do I have? What tools have we learned in the past? Okay. So it turns out that for this guy right here, and you may have tried this, it's helpful to make a difference table actually. Because if you notice, taking the first differences, here the increase is 11,000, which is very interesting. And here the increase is 12,000, and here the increase is 13,000, and then 14,000, and then 15,000. It turns out that the difference column here is almost identical to the outputs for the original function, okay? Except just a slightly, it's just been shifted up, right? And we know then that these differences aren't constant yet, but if we just keep going until the differences are constant, then we have some tools we've learned to be able to figure out a closed form rule for this. Now notice these second differences are all constant at 1,000, right? And that means we can stop and be ready to make a rule. So let's remind ourselves what we've done in the past for making a rule. Since the second differences are constant, we know that f of t is going to be a quadratic at squared plus bt plus c. Okay? Now, you may not remember this, but there is one important fact, I guess, to help us find a, and we proved this at another point when we learned all about difference tables, but it turns out that that a value is always half of the constant second difference, okay? Now that's only for quadratics. That doesn't work for linear or cubic or any other polynomial. It's only for degree 2 polynomials. So we know the a value actually happens to be 500, okay? And another easy one to find is, remember, if you plug in 0 for t, those are all wiped out, and it just leaves me with c. So we can look at t equals 0 and see that output to find c. So we know it's going to be plus bt plus 10,000. Does that make sense? And I missed my square there. Okay? So the only thing remaining to find for this closed form rule would then be the value of b, the coefficient on the linear term. Okay? But the good thing is, since we already know everything else here, we can really just plug in any t and big F of t value that I want to finish solving this. So an easy one is just 1 and 11,000. Using 0 wouldn't work because that's going to eliminate this when you plug 0 in for t, right? So let me just go work over on the side here because I'm almost running out of space. And let's use this one. 11,000 equals 500 t squared, we're going to use t equals 1, right? Times 1 squared plus b times 1 plus 10,000. And this just turns out to be a pretty easy equation to solve because this just becomes 500 plus b plus 10,000 equals 11,000. And let's see, if I subtract 10,000 from here, I get 1,000, and then subtract 500, I actually get 500 again, and 500 equals b. So it turns out a and b are both 500, and we get 500t squared plus 500t plus 10,000 is my function for the accumulation under option 1. Does that make sense? So let's go ahead and look at function g of t. And again, what I'm going to encourage you to do is to pause and try to work it out for yourself, or at least remember kind of how to do this. I'll give you a little hint here though. This one, there's not like an official method or way of figuring out what this one is, like we had a nice methodical way we've learned here. Now you may learn a different way to find ones like this, but either way, this should be what you come up with. Let's go ahead and do this. The accumulation here as well, again, I just start out with 0.01, right? And 0.02 added on to that gives me 0.03 plus I guess I should just talk about cents. 7 cents total, right? 1, 2, 4, 1, 2, 4, 8. Adding 8 to that is going to be 15 cents. Adding 16 is going to give me 31 cents. And then finally, 63 cents. So again, I told you, like I said, you can try to make a difference table here, but remember, since this is exponential growth, we've learned that it's really just polynomial growth that is very helpful to use a difference table for to like actually find the function. Now, a difference table is still interesting here. There's actually the same thing will happen if you make the difference table here. You'll see that the outputs for little g of t actually are the same as if you made a difference table. But as I said, we're going to do this a little differently. So again, pause now, play with it a little bit. So let's go about this. Here's what I'm going to do here. Okay. First of all, they're all like decimals, and in fact, they've all got a 0.01 involved. So I'm actually going to just like rewrite each of these outputs as 0.01 times something, because I notice that that's just happening in each one of these. So let's just see what happens. This is 0.01 times 1, I guess, and this is times 3, and times 7, and 15, and then 31, and then 63. Now again, this takes a little bit of creativity to think through this, but if you look really carefully at 1, 3, 7, 15, 31, 63, do me a favor, add 1 to each one of these and see what numbers you get, a very familiar sequence of numbers. You should notice that if we add 1 to this, it actually is 2, 4, 8, 16, 32, 64. It turns out that these right here are all 1 less than a power of 2. So we can actually generalize this. It might help you if we just kind of put a t down here, and then the actual rule, it seems like it's going to have this constant 0.01 involved, and it seems like there's going to be a power of 2. But the thing is, let's see what power of 2 this is, right? This is 1 less than, maybe I'll just do a few of these in the middle because I'm using up my space here. But it seems like 0.01 times 2, that's 2 to the third minus 1, right? 8 is 2 to the third. 7 is 1 less than 8, right? So these are all 1 less than a power of 2. Well, notice that t is 2, and this is 2 to the third. Does that make sense? So let's see the next one. This is 2 to the fourth minus 1, right? 15 is 1 less than 16, which is 2 to the fourth. And again, the t value and this exponent are related. The exponent's 1 more. So it seems like we're getting to this. 0.01 times 2 to the t plus 1, right? Whatever year I'm in, add 1 to it. That's what it seems like we're doing here. And the next one too. 32 is 2 to the fifth, and 31 is 1 less than that, right? And so 5 is 1 more than 4, so t plus 1 minus 1. So I think we found our formula here. It took a little bit of work, but I think we can say that g of t is equal to 0.01 times 2 to the t plus 1, and then all that minus 1. Okay, so what we've got here is a formula for capital F of t and capital G of t. And what we're going to do next is we're simply going to go to a graph. Now that we have these two formulas, I certainly do not want to try to attempt to do those by hand, right? And again, we're going to do the same process. Where do those two graphs, where does this graph and this graph actually cross each other? And hopefully they'll actually tell me the real answer to the original problem with the accumulated totals instead. Okay, so we've returned to Desmos here. We still have examples 1 and 2 up here, so I'm going to collapse those, and I'll click over here on this file icon, and it will close those off. So we'll just leave it as it is, and let's go ahead and click Add again, and I'll click a new folder myself, example 3. I'm going to press enter. Now let's do our accumulation functions, our total functions. So the cool thing is Desmos does recognize when you use a capital that you're using a different function than the original. So I've got 500x squared plus 500x plus 10,000. And that is visible here. And we can even see we've moved it up the y-intercept to 10,000 as we'd expect. And of course, it's a parabola shape. Let's go ahead and type in our other function. Capital G of x equals 0.01 times, now it's important I use parentheses here because it's 2 to the power of, and I have to use parentheses again. If I try to do x and then do a plus here, it automatically puts it afterwards. So I'm going to do parentheses and then do x plus 1, oops, 1 in there, and then do minus 1 at the end. And there is capital G of x. And let's just color code these the same as we did for the other ones. So we can see that this one remains exponential, actually, the accumulation function, but this one is not linear anymore. It's actually parabolic, as we talked about. And just like with the last example, negative t values don't really make sense. And so we're really just looking here. But again, since we're looking for when is my total inheritance going to be higher, well, clearly in the beginning, option 1 has a much higher total inheritance. You know, we can click on here and actually see. So right here, it looks like at after 8 years, there's I will have $46,000 that has come out of my option number 1. Whereas if I try to find 8 years here, I've only got about $5.11. Okay, so if I really want to, if I'm able to be patient, I can catch up. So let's do the same thing as before, except it looks like 50,000 is not zoomed out enough. I think I tested this out, and 500,000 seems to be a good option here, and it looks like it is. So let's just look this up. I don't know what you thought if you were thinking that the accumulation was if it was gonna add up quicker than the actual year itself, right? Because remember, it was almost just under 22 years that our amount per year equaled out. But now we're talking about where's our total accumulated money going to equal out, and of course that's growing much quicker because we're adding all the money together we've gotten so far. So this guy takes actually longer, almost 24 years before the option 1 is no longer the better option, which is almost at my 26 years. But I want you to think about something still here. 26 years is right here, okay? And you can tell that by the time this exponential hits 26 years, that's going to be so much higher already for option 2 than option 1, that it's very clear if I wait out the full 26 years, I'd be much better off choosing option 2, of course. So we can get back to the whiteboard and just take a look at this one last time, and then we'll be done with our lesson. We just finished looking at the graph on our graphing tool, Desmos, and essentially we see that this guy's f of t is parabolic and then g of t is exponential, and the exponential does catch up, but it actually takes almost 24 years to catch up, right? But then it grows really fast after that. So like we said, 26 years, if we have a whole time, it's still better to choose that option 2. But let's answer this final question here. As I said, the same questions. So when is f of t less than g of t? Well, we can see that f of t is less than g of t once I've passed this 23.871. So my solution for this is going to be once t is greater than 23.871. That's when option 1 is actually less. It is greater than the other one from 0, because remember 0, anything negative doesn't really make sense in our domain. So 0 up till this, right, including the 0, 23.871 is when our option 1 happens to be more than option 2. Okay, so there's a very important use of adding up outputs. And it actually turns out to be a very handy tool for a lot of things, and I already hinted at you that actually this is a really big thing in calculus. So anyway, our Our next lessons we're going to do are going to revolve around adding up the outputs in a function and actually trying to build a formula or a function out of that.